So the person who was teaching right before this told me that they weren't able to get the projector to work, and they called someone to come and work on it. If you have your computer with you, please go ahead and pull up the slides for today, which will be chapter 2, and the quiz, and both of these things are in Canvas. If you have trouble finding them, let me know and I can help you find them. Because if I have the same problem that guy had, then I'm not going to be able to project.
Do you know which slide?
53. Can the people who are dialed in through Zoom, can you see my screen and can you hear me?
Yes.
Yes.
Okay, great. So for the people who are here in the room, were you able to find the quiz?
It just has the quiz one.
Yeah, go ahead and open that up. And it should be the answer key. That's what we're going to go over first. Okay, so the projector is not finding the computer, so I'm having the same problem the other guy had. So I apologize for that. You'll have to just look at your screen and then kind of bear with me as we go through, okay? So, sorry. Okay, we'll go ahead and get started. What I'd like to do today is I would like to talk about the quiz a little bit, and then talk about what we have coming up. So the quiz was interesting in that when I looked at the grades for the class, we had 50% of the class got either an A or a B on the quiz. And then we had 40% of the class got a D or an F, and then 10% a C. That kind of what I'll call a bimodal distribution, where you have two kind of clusters of data, is kind of unusual. Usually you don't see that. Usually you see more C's in the middle, and then you see some A's and some lower scores and that. So we're going to do a few things a little differently in the class to try and get that distribution a little better. A couple things I would say though. If you are someone who got an A or a B on the quiz, congratulations, good job, keep it up. If you're someone who didn't do as well as you had hoped on the quiz, we'll talk about the upcoming test and some things you should focus on when you study. But also don't get too upset about it. You know, put it behind you and work on the next quizzes, because we have 4 more quizzes to go. We have 5 exams. We have a final exam. So there are a lot of points out there that are available for you to bring your grade up. And remember, you also get to drop your lowest quiz and you get to drop your lowest exam. So if you're doing great, that was, I say good job, but don't get too confident. If you didn't do as well as you would like, try not to focus too much on that and focus on improving and moving forward. So one of the things I want to do today is I want to go through the quiz and talk about the questions and the answers to make sure that everyone not only knows what the correct answers are, but kind of understand why those were the correct answers. So what I have on the screen is the answer key for your quiz. The first question is, a combination of sand, salt, and water is an example of what? Choices are homogeneous mixture, heterogeneous mixture, a compound, pure substance, or a solid. If we think about what a homogeneous mixture is, that's where we're saying everything is the same in that mixture. Heterogeneous mixture tells us that we have different things and different, some may be solid, some may be liquid, things like that. And if you think of sand, salt, and water, that's kind of like the mixtures that we'll be dealing with in the lab this week, where we have a solid material that has sand and salt, and we put it in water. And what we see there is we see that we don't have a homogeneous mixture. So question 1, that combination is a heterogeneous mixture. Okay. Okay, question 2. Which one of the following has the element name and symbol correctly matched? We have Na, sodium, tin, iron, neon, and bromine. So Na is sodium. So that's the correct one. Does anyone know what tin is? Tin would be Sn. How about iron? Anyone know what iron is? Iron's Fe, correct. How about neon? Ne, right. And then bromine. BR, right. So whether you got this question right or wrong, you want to make sure that you're memorizing those element symbols and names so that whichever one of those or some other one, if that would have been on the exam or the quiz, then you would know that. You want to get to the point where you don't really have to think too much about it, that it just kind of becomes second nature. It's almost like learning the alphabet. You don't think about what is C or what is B or something like that. You know it so well that it just is second nature to you. So question 3, which of the following is often separated into components by a simple technique such as filtering? So we've done some filtering in lab, and what have we used filtering for? What is that good for?
Separating solids and liquids.
Right, separating solids and liquids. And if we have solids and liquids, then that's a heterogeneous mixture. We talked about that a little bit in the first question. So the answer here is A. If you recall, the example we had in class was if you're making spaghetti, you have the noodles in the water, you boil it, and then what do? You pour it through that strainer. That strainer is just another type of filter, and it separates the liquid, the water, from the noodles. Number 4, the law of constant composition says composition of a compound is always the same. All substances have the same composition. Composition of an element is always the same. Composition of a homogeneous mixture is always the same. And composition of a heterogeneous mixture is always the same. So this law of constant composition tells us that a compound's composition is always the same. So what that means is if you have a sample of water, that's always going to be H2O, whether it's in a beaker or whether it's in a bathtub or whether it's in a lake. If it's water, it's always H2O. That composition doesn't change. Okay, of the following, which one is a chemical reaction? Melting of lead, dissolving sugar in water, tarnishing of silver, crushing of stone, dropping a penny into a glass of water. When we say something is a chemical reaction, what are we saying is happening? We're saying that the substance or compound that we're starting with is chemically changing. So we just talked about the law of constant composition, where we said for that law to be true, we're saying that the compound composition doesn't change. In a chemical reaction, we're saying the opposite. We're saying that that composition does change. So when we look at these choices, we're not looking for just physical changes, although it can have a physical change. What we're really after is the chemical composition changing of whatever it is we're looking at. So melting of lead, there, we're not changing the lead atom. We're just changing the form of the lead. So it's going from a solid, and then we're melting it, so it's becoming liquefied. If we take sugar and we dissolve it in water, we're not reacting with that sugar molecule. We're not changing the composition. We're not violating constant composition, that law. Sugar is still sugar, it's just changed its physical form from being a solid into a liquid phase. Tarnishing of silver. Well, if silver is tarnishing, that's an oxidation reaction. And so that silver there's actually a chemical reaction going on. So because there's a chemical change occurring, that tells us that it is a chemical reaction. Crushing of stone, once again, we're not doing any reaction of the components in the stone. We're just changing the physical nature of it. And then finally, dropping that penny into a glass of water. Water is not a reactive substance towards a penny. So the penny is going in there, but it's not changing its chemical composition. So when we're trying to decide if something is a chemical reaction or not, What we're trying to decide is, are we changing the composition of the stuff we started with? If the answer is yes, then you have a chemical reaction. If it's no, it's more likely just a physical change. Okay, number 6, which of the following is not an intensive property? So the first thing we would want to know is what is the definition of an intensive property? Does anyone remember that?
It's like inherent.
Independent.
Like this, the compound or element reacts this way. It's not like situation by situation where like I have more of this time.
Yeah, intensive simply means that it's independent of the amount of the stuff you have. So whether you have one small amount, if you have 1 gram or 1 kilogram, it doesn't matter. That property will be the same. So extensive is the one that depends on the amount of stuff that you have. So when we look at these choices, density, well, density is defined by mass per volume, right? So that doesn't change. Density for a compound doesn't change, whether you have a little or a lot. Same with melting and boiling points. Those are values that are based upon what the compound is, not how much you have. So then that leaves mass. And if you think about it, mass, well, mass by definition is how much of stuff that you have. And so, you know, you think of when you're in the lab, you go to the balance to determine the mass of your sample. So that's directly dependent upon how much of the stuff you have. So in 6, the answer is D. Mass is not an intensive property, and it's an extensive property. Number 7, we have another chemical process question. And remember, we said before that the chemical processes are the ones that there is a chemical change, so that compound that we started with undergoes a chemical change. And so we look at our choices. Rusting of a nail. Well, we know from the previous question that oxidation process of rusting, that's a chemical change. Freezing of water, is that a chemical change? Right, it's not. It's just a physical change. So we're going from a liquid state to a solid state, but if we look at the molecules, they're still H2O, they're still water. No chemical changes occurred. Decomposition of water into hydrogen and oxygen gases. So there we're telling you that there's a change. H2O is becoming hydrogen and oxygen. So that's a chemical change because we've modified what that starting compound is. And then finally, compression of oxygen gas. There, we're just taking a certain volume that the gas is in, and we're kind of squeezing it down, we're compressing it so that it fits into a smaller volume. Haven't done anything to the oxygen gas itself, we've just changed the volume. So that is not a chemical process. So the correct answer is C, 1 and 3, the rusting of the nail and the decomposition of water. Number 8, accuracy refers to how close the measured number is to 0, how close the measured number is to the calculated value, how close to other measured numbers, how close to the true value, how close to infinity. So we said that accuracy is how close it is to the true value. What did we say precision was? Does anyone remember that? We said,
How many times you got the result?
yes, so precision is how close it is to the other measured values. So in other words, if we repeated an experiment, say 3 times, how close those 3 values were to each other would be an indication of the precision. The example we had, kind of cartoon example we had, was the dart thrower. So, you know, if you're trying to hit the bullseye, so if you're hitting the bullseye, you're very accurate. But by the same token, if you're very precise, then each of those darts would be on top of each other. They would be very close to each other. So in this case, we were asking about accuracy, so D is the correct answer. How close is a measured number to the true value? You hear people use accuracy and precision interchangeably all the time, and you really shouldn't, because they are two different things. Number 9, which of these is the abbreviation for milli? So if you think back to the when we were going through the chapter 1, we had a table where we had all of these prefixes. And one of the things that's really important, not just for this quiz or the first exam, but going forward in the semester, is memorizing those prefixes, because you need to realize, in this case, milli is the small m, but if you have a K or a capital M or an N or a D, knowing what those stand for tell you what type of exponent should be. So if I say something's a kilogram, how many grams would that be? Kilo is 1,000, right? So then I would know by seeing that kg that what I'm really talking about is 1,000 grams. So here, if I said milligrams, then I would know that milli is 10 to the minus 3 grams. So that's the kind of stuff that you're going to need to memorize for both what we're working on now, but that will carry through as we go on through the semester and even beyond there. So for number 9, the answer is B. It's the small m. Okay, one of the things that we talked a fair amount about was density calculations and how to use density to figure out some things about compounds. And if you think about the first lab that you did in the lab portion of the class, that lab, we did some density. You did a density plot, you did some calculations based on density. So you kind of saw the value of how density can play to figure out weights and volumes and things like that. So before we go through number 10, the math on it, I have a question for you. Did everyone remember that centimeter cubed is the same as mils, and that centimeter cubed and cc and mils are all the same? So you'll see density expressed, it's always weight per volume, but sometimes it's expressed grams per centimeter cubed. Sometimes it's grams per mil, sometimes it's grams per cc. All those things mean the same thing. So once again, this goes back to the table that we talked about that showed some of these prefixes and what some of these things mean. So in there, we had the information that a milliliter is a cubic centimeter, and so that's why those are equivalent. So that's very important that you remember, because you'll see density expressed different ways. Just remember that those are the same. So when we talk about this, in this problem, we want to get to grams in our final answer. So this is where we're going to use dimensional analysis to help us figure out how to do this. We see that we have a density, 19.3 grams per centimeter cubed, or grams per mil, however you prefer to think of it. But we see that the volume of the gold nugget is 0.00369 liters. Our density is in mils, grams per mils, not grams per liter. So the first thing we have to do is we have to convert that liter value into milliliters. So how do we do that? That's where we have to remember that 1 liter is 10 to the 3rd mils. So then if we do that math, we cancel our liter units. So we have the 0.00369 liters times 10 to the 3rd mils per liter. We see our liters cancel, and then we wind up with 3.69 mils. Now that we have that volume in the right units, we can set up our density and use the density that they gave us, the 19.3. If we multiply 3.69 mils times 19.3 grams per mil, then the milliliters cancel out and we get our units of grams, which is what we want. And so the final answer is 71.2. And like I said, one of the key things is remembering that mils equals centimeter cubed equals cubic centimeter. The other thing was realizing you needed to convert that liters into mils. Okay, number 11, 1 nanometers equal how many picometers? Well, here you needed to remember that a nanometer is 10 to the minus 9th meters, and a picometer is 10 to the minus 12th. So if you know that, then you can convert the nanometers to meters and then meters to picometers and get 1,000, which the answer there is A. So this is remembering what these prefixes, what pico means, what nano means. And one thing, you probably have figured this out, but I'll just say it anyway, is you notice that these prefixes vary by 10 to the third. So pico, nano, all those, when you go down the line, they go by 10 to the third. The way I always remember it is, nano is the easiest one for me to remember because nano, 9. And nano, you hear like nanotechnology and you hear nano whatever, you think of something small. So I think 9 small, okay, I'm at 10 to the minus 9. And then I go from there, and pico is the next one on the list. So that must be the 12th. And then femto, and then on down the line. And going the other way, micro is before nano, so that's -6. Mill is before that, to the -3. So take a look at that table and note that they vary by 10 to the third. And if you can really memorize a couple of those and then kind of by association link the others, I think that can be helpful as you're starting to learn what these are. So number 12, the initial or tentative explanation of an observation is called what? So we have law, theory, hypothesis, experiment, test. So for this one, we're trying to have a tentative initial explanation of something. So most people would pick either theory or hypothesis. In this particular one, the answer is hypothesis, C. Why is it hypothesis and not theory? Does anyone remember that? Because you're observing, right. Remember when we kind of talked about that process of figuring this stuff out, we said that it kind of starts with just making some observations. And you see something and you make some, what I would just call guesses as to what is going on. And that's your hypothesis. To get to theory, that means you've actually started doing some experiments and have some actual data, not just observations. So that's the big difference in those two, is if you have some data, if you're starting to collect data, then you're starting to be able to come up with a theory. You may change that theory as you get more data, but you still have a theory because you have something behind it. The hypothesis is just more or less what you see and you come up with an opinion on it or a thought on it. And so you say you hypothesize that, but that's before you've actually started doing anything other than observing. Okay, 13. What's the answer to this math problem? The key here is getting the right number of significant figures. So 2.01 times 6.936, that divided by 12. So when we do multiplication and division, how do we determine how many significant figures that we're going to use? Well, we look at the number that has the least number of significant figures, and that's the number that will drive what those significant figures are going to be. In this case, 2.01 has 3 significant figures, 6.936 has 4, and then 12 has 2. So what that tells us is that 2 significant figures is going to be the driving force on this. So if we do the math, then it becomes which of these numbers is the correct number of significant figures. And since we said 12 with 2 significant figures defines how many we have, we can only have 2 significant figures in our answer. So that's where we wind up with B, which is 1.2.
That's all when we multiply and divide.
That's when you multiply and divide. Do you remember what it is when you're adding and subtracting? So when you're adding and subtracting, you look at how many significant figures you have to the right of the decimal point. So like 1.234, so it'd be that 0.234. And then if the numbers that you're adding and subtracting, you'll only have the number of places past the decimal of the lesser of the numbers, the least one. So if one has 4 digits past that decimal and one has 2 digits past that decimal, your final answer will just have the 2 digits past the decimal, okay? So multiplying and dividing is just which number has the fewest significant figures. Adding and subtracting, it's looking how many digits past that decimal point you have, and the number you're dealing with that has the fewest of those will determine how many you go past there. Okay, so slightly different rules depending upon which kind of mathematical calculation you're doing. Okay, 14, the density of a 167.4 gram sample of magnesium has a volume of 96.32 mils. So what is that density? Well, once again, density is weight per volume. And we need to remember also that even though they give it to us, the volume in mils and centimeter cubed mean the same thing. So here we want to take our weight, 167.4 grams, and divide it by the 96.32 mils to give us 1.738 grams per mil, or grams per centimeter cubed. So the answer for that one was E. So key here, remembering what density is. Density is weight per volume. And then remembering that centimeter cubed and mils are the same. Okay, now the last question. This was the most difficult question on the quiz. What you needed to be able to do is you needed to be able to figure out what form your answer needed to be in. And they tell us it's grams per centimeter cubed, so grams per centimeter cubed, grams per mil. So it's that density value. And the big thing is we need to get our dimensional analysis lined up so that the data that they give us, we can get into that form so we can have mass per volume, grams per mil. So let's look and see what information was given to us. We're told there's 4.369 grams of metal. We're told that that's placed in a flask. Then water was added to the flask. And now we have a total volume of 126.4 mils. So this is kind of similar to what we did in the first lab, where we used water displacement to understand how you use that information to get kind of unknown densities. So then they tell us that we have the mass of the water, the flask, and the metal, and that's 268.5 grams. Then we're told we have a mass of the flask of 139.3 grams, and that the density of water is known to be 1 gram per mil. So that's what we have to work with. Well, let's take a look first at what we know. We know that we have a total weight of water, flask, and metal of 268.5 grams. If we know we have the weight of the flask, that's 139.3. So if we subtract those two, then now we know what the weight of the water and the metal is. But we know the weight of the metal, that's 4.369. So if we subtract that weight of the metal from that total weight again, then we know how much water in terms of grams that we added. So we had one weight, one piece of data, which was the weight of the flask, the water, and the metal. Then we had a piece of data that told us how much just the flask weighed. And then we had another piece of information that told us how much the sample weighed, the metal weighed. So we know that that 268.5 is the sum of all three of those things. So if we subtract the flask and the metal from it, then we get 124.8 grams, and that's the weight of the water. If we know the weight of the water, we were given the density. And so by converting that grams of water to mils using the density, and here it's a trivial calculation because it's 1, but if it wasn't 1, then it would be mils of water or mils of the solution divided by the density if it was a different solvent. And then that would convert it over to mils. So now we've got how much water that we put into the flask. Well, what we're after is density of the metal, right? So what do we need to get density of the metal? We need to have the weight of the metal, and we need to have the volume of the metal. Well, the weight of the metal we were given in the problem. That's the 4.369 grams of the metal. So we need to figure out the volume of the metal. Well, we were told that the total volume after you added the water was 126.4 mils. So that's going to represent the volume of the water plus the volume of the metal. Well, we just calculated the volume of the water, right, from those weights and the density of water. That was 124.8. So if we take 126.4, which was water plus metal, and then subtract out the volume of water that we just calculated, that's the 124.8, now we get 1.6 mils is the volume of the metal. So great, now we have weight of metal that was given to us in the problem, that's the 4.369 grams, and we divide that by our volume of metal, 1.6 mils, excuse me, and then we do that math and we get 2.7 grams per mil. So why do we have two significant figures there? We have two significant figures because the grams has 4 significant figures, the mils has 2 significant figures, and since we're doing a multiplying or dividing mathematical process, we go by the number that has the fewest number of significant figures. In this case, the 1.6, so that's 2 significant figures, so we want 2 significant figures in our answer. And that's how we get to the 2.6 grams per mil, which was answer D in the answer list. So to solve this problem, you had to do a few things. One is you had to think about what units do I want and how do I get there? Then you had to think about, well, okay, how do I get, I'm given the grams of metal, how do I get that volume of metal? That's really the tricky part of the problem. And so by looking at the information you were given some weights of total weight of flask and water and metal. You had a weight of a metal, you had a weight of the flask. By using that information, you could get a weight for the water, convert that weight of water from a grams value to a mils, a volume. Then by knowing how much water was there and knowing the total of the water plus the metal volume, you could then get down to that volume of the metal. And then once you had that information, then you could go ahead and calculate your density. So you had to do a few things there. Some people were able to do it, so congratulations to those of you who did. The other, if you weren't able to do it, that's okay. Take a look at it. And what you do here, and like I said, this is similar to what we did in the first lab, is it's using dimensional analysis, using density, using some of these some of these concepts and then applying them to solve a problem, okay? So it's one thing to just take a certain number of grams and divide it by mils and calculate a simple density like that. That's not normally how you would you would do this type of stuff. It's more like what we did here in this last problem. Any questions about anything on the quiz? Okay. So, the next thing that we're going to do is we're going to finish up chapter 2. And before we do that, I just want to talk a little bit about what's next in the class. So we were supposed to have an exam on Monday. We're going to push that back to Wednesday. So what we're going to do today is we're going to finish up chapter 2 now that we've reviewed the quiz. We're going to finish chapter 2. There'll be some homework problems at the end of 2. I'd like you to work on those between now and Monday. And then on Monday, what I'm going to do is we're going to go back through chapter 1, and we're going to go through chapter 2, and we're going to review things, okay? And we're going to go through and talk about the things that are really critical that you learn out of those 2 chapters. And then we'll have our first exam on Wednesday of next week. And that exam will cover chapters 1 and chapter 2. So go back, take a look at the quiz, make sure you understand not just what the right answer is, but how you go about thinking about the problem to get to the answer. Spend some time on chapter 1 going back and looking at some of those tables of prefixes and conversion factors and things like that so that you're comfortable with that. Make sure you know the symbols for the elements, stuff like that. And then in chapter 2, as we're about to finish that up, you'll see, lucky for you, more memorization. There's a lot of stuff in both of these chapters that, to be honest, you just have to memorize it. But it's important that you do, because you'll use that information as we go forward in this semester and in next semester as well, okay? So let me change over to the slides. Okay, can the people on Zoom see the slides now?
Yes.
Okay, thank you. Okay, so chemical nomenclature. When we talk about how we name compounds in chemistry, we call that chemical nomenclature. And so what we're going to talk about next is we're going to talk about how we name ionic compounds, acids, some binary molecular compounds, and some simple organic compounds. And the organic compounds that we'll look at are alkanes and alcohols. If you continue on in chemistry and take organic chemistry later, you'll learn a lot more about naming organic compounds. They kind of have their own set of rules in that. But we'll do a little bit of that today. Okay, when we talk about inorganic nomenclature, there's a few things to remember. One is we write the name of the cation. Does everyone remember what a cation is? A cation is the positively charged ion. And when we write it, that's always written first. Some cations, not all, but some cations can have more than one charge. And so we'll talk about that later in more detail of why that is. But sometimes it can be +2, sometimes it can be +3. So depending upon what it is, we often write that charge in parentheses, the Roman numeral 2 or 3 or whatever it happens to be. If it's a polyatomic cation, it will end in IUM, EUM. And a good example of that is ammonium. So you think ammonium ion is NH4+. So that's a polyatomic cation because the cation has nitrogen, and it has hydrogen. So polyatomic just means it's more than one atom. If the anion is an element, we change its ending to "ide." So for instance, if it was sodium chloride, NaCl, so there the anion, and remember anion is negatively charged, so that chlorine anion would be called chloride. If the anion is polyatomic, we just write the name of what that polyatomic ion is. So for instance, if you had sodium acetate, you'd have sodium as the cation, that'd be the positively charged part, and then acetate would be the anion, and that would be the negatively charged part. So a couple of rules for naming inorganic, simple inorganics. Okay, when we start introducing oxygen ions into it, or oxygen atoms into the ion, it gets a little more complicated. And the next couple of slides will go through some examples of that. This stuff can be a little bit confusing, so you're just going to have to take some time and memorize kind of the rules around it. So if you have two oxyanions involving the same element. So what do we mean by oxyanions? So here we see the two examples. One is nitrogen containing and one is sulfur containing. The first one, nitrite and nitrate, the oxyanion is the nitrogen with oxygens. The first one has one nitrogen, two oxygens, and that's nitrite. And then the second has one nitrogen, three oxygens, nitrate. When you have pairs like this of the same elements, but different amounts of oxygen, the one with the fewer oxygens is always ite. The one with the greater number of oxygens is always ate. So in these two examples, the NO2 versus NO3, the fewer oxygens, the NO2 is nitrite. The greater number of oxygens is nitrate. When we go to the sulfur-containing one, we have SO3 and SO4. Once again, the fewer number of oxygens means it's sulfite. The greater number of oxygens is sulfate. So when you have this where you have an atom with certain number of oxygens on there. Remember, when you have a pairing like this, the one with the fewer number begins with "ite." The one with the greater number ends with "ate." So this is where we get nitrite, nitrate, sulfite, sulfate. These 4 ions are pretty common ions, so you'll see these over and over again. Okay, there are some patterns that you can see with these oxyanions. And this goes back to, remember we talked about periodicity of the periodic table, and so we can learn some things about the atoms and about ions just by how they line up in the periodic table. Okay, if we look at this, if we remember, periods are the rows across and groups are the columns, if we think back to the periodic table. And a couple things we see. One is we see that in the periods, as we go from right to left, the charge increases. So looking at that period 3, we see the perchlorate ion has 4 oxygens, 1 chlorine. The sulfate, 4 oxygens, 1 sulfur. Phosphate, 4 oxygens, 1 phosphorus. So same number of oxygens, and then same number of the other atom, but the charge is different. And we see as we go from right to left, we see it increasing. So that perchlorate just has 1 negative charge. The sulfate, 2 negative. Phosphate, 3 negative. So that's a trend that we see across the period. We see the same idea in the period 2 above it with the nitrate and carbonate. There you have 3 oxygens and then 1 other atom. But yet the charge as you go from right to left and there goes from -1 to -2. The other thing that we see in this is in that second period versus the third period. In the second period, we're able to have 3 oxygens bonded to the atom. In the third period, we can have 4 oxygens bonded to the atom. So if you're in that period 3, and you're trying to think, what's my oxyanion going to look like? We know that those period 3 atoms like to have 4 oxygens bonded to them. Period 2, only 3 oxygens bonded to them. So this is some of the trending that we can get by looking at the periodic table to give us a feel for, okay, is phosphate PO4? Is it PO3? Is it whatever? Okay. The chlorate related ones to me are the most confusing because you got a lot of options here. So let's take a look at this for a second. We talked about if it's a simple anion, chlorine, you add the "ide" to it, it becomes chloride. So there we see that simple anion would be chloride, just as it would be bromide or something like that. But it's that simple, no oxygens involved, chlorine becomes chloride, adding that "ide" to it. Now, when we start adding oxygens, we see with chlorine, there's a lot of ways that can form, ranging from looking on the right, we see 1 oxygen, then we have 2 oxygens, 3 oxygens, 4 oxygens. So there's 4 different versions of this chlorine, oxygen, oxyanion that we can have. There's a couple things you notice too. They're all -1 charge, and the names change as the number of oxygens change. So over on the right, where we have 1 oxygen, it's hypochlorite. Then 2 oxygen is chlorite, 3 oxygens chlorate, 4 oxygens perchlorate. So the one with the fewest number of oxygens ends in "ite." That, in this case, that's the hypochlorite. Then we add an oxygen, the next one up, we get up to 8 with the second most. And then the fewest one also has the hypo in front. So we have 2 ites for the low ones, 2 eights for the 3 and 4, but we distinguish them by having hypochlorite for the 1 oxygen and perchlorate for the 4 oxygens. Per is another way of saying 4. Let's talk about acids for a little bit. So when we have an anion in the acid that ends in "ide," so chloride, bromide, something like that, then we change that "ide" to "ic" and add a hydro in the beginning. So in the examples we have here, we have HCl, hydro, it's chlorine, so chloro, and we add the "ic" to it. So hydrochloric acid. Same with the next one, with hydrobromic acid. And then finally, hydroiodic acid. So if it's an acid like this, hydro in the front, that "ide" becomes "ic." If the anion ends in "ite," we change that ending to "-os, O-U-S. So HClO, hypochlorous acid, HClO2, chlorous acid. So we think back to what those were in the previous slide, and that's how we get it to the OUS. And you can see in the little boxes there, it's got the chlorite anion going to chlorous acid, the hypochlorite ion, ClO minus, going to hypochlorous acid. And then finally, if the anion ends in 8, then we change it to "ic" as the acid. And the examples here, we see ClO3 chlorate becomes chloric acid, and ClO4 perchlorate becomes perchloric acid. Can be very confusing to remember. "ite" goes with "us, 8 goes with "ic." "Ide" goes to "ic." You have the hydro in front. There's no simple way around it other than just kind of memorizing the rules and practicing a little bit with the compounds, okay? So the table we have here gives us a list of prefixes that we'll need to know. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Those are telling us how many atoms are going to be in the molecule. And it can be 1 to 10, it could be more, but we're just going to worry about these 10 for now. When we name the things, the way the convention is usually you write the metal first, and remember the metals are the ones to the left on the periodic table if we're looking at the periodic table, and that's usually written first, and then there is some type of prefix to say how many are there, unless it's 1. If it's 1, we don't say mono. Then you write the anion, which is typically something to the right in the nonmetals, and we'll use one of these prefixes. If there's 2 of them, it would be di. If there's 3, it would be tri, and on down the line. And so we kind of combine all that. So typically it's the metal on the left, which is the cation. It's the nonmetal on the right, which is the anion. So for these ionic type compounds. There's also binary, if we talk about binary compounds for this type of thing, the second element is changed to an ide. So in these examples, we have one carbon, we have two oxygens, so it's carbon, di is 2, so it's carbon dioxygen, and we change that second one to an ide ending. So instead of saying carbon dioxygen, we say carbon dioxide. The next one, carbon tetrachloride, we have one carbon and we have 4 chlorines. 4 is tetra, so carbon tetrachlorine, carbon tetrachloride. Sometimes you get to where you get vowels kind of going up against each other. So in the example here, we have dinitrogen pentoxide. So normally you would think, oh, it's dinitrogen because we have 2 nitrogen, and then pentaoxide because we have 5 oxygens. We don't like to say it with the double vowel like that. So instead of saying pentaoxide, we just say pentoxide. Same with the carbon and the oxygen there. So instead of saying carbon monooxygen or monooxide, we say carbon monoxide. And the carbon monoxide is a good one to think about because most people hear about carbon monoxide. You always hear about that in your house. Oh, you don't want carbon monoxide. That can kill you if you have it. So people are familiar with that. But you never say carbon monoxide, right? And that's because of that double vowel rule. So if you can remember that to help you remember the double vowel rule, I think that would be useful. All right, let's talk about organic compounds for a little bit. When we say we're doing organic chemistry or discussing organic chemistry, we're talking about studying compounds that have carbon in them. And so the organic chemistry world has their own set of nomenclature. We're just going to talk a little bit about it here, give you some examples. As I said before, if you continue on and take organic chemistry later, you'll get the whole set of rules and things like that for those compounds. So the simplest organic compounds are what they call hydrocarbons or alkanes. And alkanes are simply compounds that contain carbon and hydrogen. And for alkanes, everything is a single bond. And the single bond in these pictures are illustrated by just having that simple line between the hydrogen and the carbon, or the carbon and the carbon. So the first part of the name corresponds to how many carbon atoms there are. So 1 is meth, 2 is eth, 3 is prop. So that's where we get methane, ethane, propane. Then, so you have the first part telling you how many carbon atoms are present. The second part for an alkane is always ane, ane. So that's how you get the nomenclature for these 3 compounds. Any idea what 4 carbons would be? Anyone know what that would be? So 4 is butyl. So if 4 is butyl, it would be butane, because but and then ane. In organic chemistry, people talk about something known as functional groups. And functional groups are just common combinations of atoms. And here we have a real common one here, the OH group. And that is what an alcohol is. So if you have an OH group on something, you have an alcohol group on there. And so the way you name these simple alcohols is you have a alkane, and then instead of ending it in ane, you end it in ol. So Methane would be the first one, so methanol. Ethane's the second one, ethanol. 1-propanol is the third, so propane, propanol. So remember, if you have that OH group on there, then it's all OL, and that's how we designate alcohols. So the propanol is interesting. So you see that that is a 1 in front of the propanol. Anyone have any idea what that 1 is there for? The 1 is there to let us know where the OH group is attached, to which carbon it's attached. And that's telling us it's at the first carbon. It could be at the second carbon also, then it would be 2-propanol. And this type of thing is something known as isomers. And here you see over on the right-hand side pictures of 1-propanol and 2-propanol, where it shows that that OH group, whether it's attached to that first carbon atom, which would then be 1-propanol, or the second carbon atom would be 2-propanol. Even though the structure is different, so in other words, the attachment of that OH functional group is different, the molecular formula would be the same for these because we haven't changed the number of carbon atoms or oxygen atoms or hydrogen atoms. When you have something like this, where the number of atoms are all the same, it's just the arrangement is different in terms of where that OH group is at. These are called isomers. So in this chapter, we have a lot of things to memorize. We have the element names and the symbols. We have naming rules for a whole bunch of different types of compounds, organic and inorganic. We have prefixes. So what I would suggest you do is take a look at some of these problems here and use that to test yourself to see how well you've memorized some of this information. It'll take a little bit of time to do, but that's really what you're going to have to do for this. What we will do on Monday is we'll go through chapter 1 again, kind of highlight the key things on that. We'll go through chapter 2, kind of highlight the key things of that. And then Wednesday of next week, you'll have your exam. Okay? Any questions about anything before we wrap up? Yes?
Is the exam going to be open now after COVID?
So as long as we're under COVID stuff, it'll be the same deal. It'll be open notes and all that, because we'll have some people who might be in the room taking the exam, some people who are taking it, you know, somewhere else out in Zoom land. So it'll be the same as the quiz. The only thing, the quiz was all multiple choice. I haven't decided if the test will be all multiple choice or not. I haven't decided that yet, because it may have where you have to actually work some stuff out, but I just have to make up my mind on that. But it will be open note, open whatever, and it will have a time factor as well. Okay. So any other questions? Okay, thank you.